Welcome everyone to this lecture series on modular forms. Um, Before we start, I have created a Discord server where you can all reach out to me. So if you are not in that Discord server, well, the link, the invite link is right here, and you have probably received an email already, right? So also, uh, you can basically send me an email, or you can basically DM me on Discord if this link doesn't work. So my email address is otonuroychoudhury@gmail.com, and my Discord is otonu #7358. So yeah, so this is these are basically the two of the most convenient ways to reach out to me. And before we start the actual contents on modular forms, I would like to make sure that we all are on the same page. So that's why I would like to review some of the basics of group theory and complex analysis. So yeah, we're starting. First of all, we shall define what is a group. So a group is basically a set where we have defined a binary operation on that set, and that binary operation obeys certain rules. So first of all, what is a binary operation? So a binary operation. Also, my handwriting is not really good at all. So if you don't understand any of my handwriting, please feel free to ask. A binary operation on a set S is basically a map, which for now I'll call the map star, and the map is from S cross S to S. So basically, these maps star, it takes two elements of the set S and it spits out another element of S. So if X and Y are two elements, and then we shall often write star of X comma Y as X star Y. So a very a basic example of a binary operation is well, addition on the set of real numbers or on the set of integers, right? We take two integers and we can add them and we get another integer. So addition on the set of integers is an example of a binary operation. Now, what is a group? So a group is basically a set with a binary operation defined on it, such that certain conditions hold. So definition, a group is a set G together with a binary operation, star on it, star on the set G, such that, well, now I'm stating the conditions the binary operation has to satisfy in order for the set to be a group under that binary operation. So the first one is associativity. So what do you mean by associativity? Basically, if I have three elements, A, B, and C in the set G, then we can apply the binary operation star on these three elements in two different ways, right? One is we can first compose A and B. By composing A and B, I basically mean taking the binary operation of A and B under star. And then A star B is an element of G, right? So then we can compose that element with C. So we could have done this another way. That is, we could have done B star C first, and by taking B star C, we get an element of the set G, and on that element, we can compose that element with A, right? So if these two happens to be the same for all A, B, and A, B, C in G, we call the binary operation associative. So this is one. The second one is existence of identity element. So what do I mean by that? There exists an element E in G such that if I compose with E any element of the set G, I get back the same element. So basically, E star A equals to A star E equals to A for all A in G. So, yeah. And the third one is inverse. That is, for each A in G, there exists B in G such that A star B equals to B star A equals to the identity element A. So is the definition of group clear to everyone? If not, feel free to ask at any point. Okay. So yeah. So I forgot to tell one thing, that is I said that for each A there exists B such that A star B and B star A both are the identity. So if this happens, we call B.
This one flickers. And this one.
Okay. So yeah, so if A star B and B star A both happens to be E, then we call B an inverse of A. So notice that I said an inverse, not the inverse. So yeah, and well, you can prove that there is exactly one inverse. So yeah, I'm not gonna prove it. I'm just gonna state it and leave it as an exercise for you. So exercise. First of all, the identity is unique. That is, one cannot have two identity elements in a group. Then the inverse of an element, well, sorry, inverse of an element is unique. And yeah, so since inverse is unique, so if B is an inverse of A, I write B equals A inverse. So yeah, and another thing, that is the inverse of A star B is the inverse of B star the inverse of A. So sorry. Yeah. Okay. Can someone give me an intuitive explanation of the third statement, that the inverse of A star B is the inverse of B star the inverse of A? The order has to be reversed. So yeah, yeah. So basically, when we put on our shoes, we wear socks first, then we wear shoes. But in case of but while taking off, I take off the shoe first, then I take off the socks. So yeah, so that's basically an intuitive idea of why the order has to be reversed. But yeah, one can prove it using the three properties of the group. That is associativity, identity, and inverse. Okay. Yeah, sure.
For the set G set of real and
Yeah.
binary operators multiplication 0.
Yeah. Well, I'm now getting into some examples. So you've stated a non-example. So yeah, I'll start with that one. So yeah. So suppose our set is R and our binary operation is multiplication. So is it a group? So first of all, let us investigate. So is the operation associative? That is x, y, z. This is equals to x, y, z. We know this is true, right? So the multiplication is associative, all right? So do we have an identity element for the multiplication? Of course we have, because the identity is the element 1. So if with any real number, if we multiply 1, then we get back that real number. But do we have an inverse element for all real numbers? For most of them we have, because if x is not 0, then 1 over x is an inverse element of x. But for this, we need x to be non-zero. So, yeah, but 0 is in the set of real numbers. So this is not a group. However, if we delete the point 0 from the set of real numbers, then we get a group. So, but r minus 0 with respect to multiplication is a group. So, is this clear to everyone? So, yeah, I have several more examples. That is, so, one. So, the second example is the set of integers with respect to addition. Is it a group? Well, yeah, it is a group because the addition is associative, obviously. We have an identity element that is 0. Why is 0 an identity element? Because with each integer, if we add 0, then we get back that integer. And the inverse element, well, yeah, the inverse of the element n is negative n. Right? Okay, so this is a group. Okay, is the set of natural numbers a group with respect to the addition? With respect to addition? No, it's not. Well, if we take a natural number, for instance, 1, then the inverse element has to be negative 1, which is not in the set of natural numbers. Okay, so this is not a group. All right. So think about the set of all invertible n times n matrices. Invertible n times n matrices. So yeah. So with, let's say, real entries. So this set is known as GLNR, or some textbooks write GLN, R, like this. So GL stands for general linear group. Well, I already said it's a group, so yeah. So this set is a group with respect to matrix multiplication. Okay, I'm not going to verify it because, well, it's left as an exercise that this is indeed a group. And the group we shall be dealing the most in this class is this one, SL2 set. So what is this group? This group is the set of all 2 by 2 matrices with integer entries. A, B, C, D are integers. And the determinant of this matrix is 1. That is AD minus BC equals to 1. So this is the group we shall be dealing the most in this class. Yeah, so again, checking that this is indeed a group is left as an exercise for everyone. Okay, so far, do you have any questions? All right. Okay, so yeah, now I'm defining subgroup, that is definition subgroup. So suppose G is a group and H is a subset of G. So when I said G is a group, I meant that G is a group with respect to a binary operation, right? So I'm not going to write all the time that G comma star is a group when the context of the binary operation is clear, but yeah. So suppose G is a group with respect to the binary operation star, and H is a subset of G. Now, if H happens to be a group as well, under the same binary operation, then we call H a subgroup of G. So if H is a group under star, then H is called a subgroup of G. So what are the conditions that we need to satisfy for H to be a group?
Like it's already associated.
Yeah, so
Inside the G.
exactly.
We just have to check the identities there and versus all.
So we need to check that the identity is there, and for each H in H, H inverse is also in H. Well, yeah. So this little symbol here, the upside down A, is read as for all, or for each. Yeah. But we need to check another condition. That is, if we take two elements, H1 and H2 in A, then the composition of H1 and H2 also has to be in H. Right. Why do we need to check this? Because, well, H1 and H2 are elements of H, so they are also elements of G, right? Because H is a subset of G. And a priori, we don't have any information about the composition H1 star H2. We only know that H1 star H2 is in G. So we don't yet know that it's in H. So yeah, for yeah, all H1 and H2 in H, this composition has to be in H as well. So if these three conditions are satisfied, then we call H a group, a subgroup of G. Okay. Okay, so let's consider the group of integers. Can someone tell me a subgroup of this set, of this group?
Even integers.
Yeah, the operation is addition. Yeah, even integers is a subgroup of this of Z. So the set of even integers is sometimes written like this. That is, all the elements of the form 2n such that n is in Z. Okay, so this is a subgroup of C. All right. In fact, any nz, that is any, so nz is the set of all the multiples of n, where n is a non-zero natural number, so non-zero integer. So any nz is a subgroup of Z. So
discussing subgroups, do we always need to maintain a proper subset or the normal?
well, no, it need not be a proper subset. So Z itself is a subgroup of Z. But such conditions are not really interesting. So for practical purposes we generally have that the subgroup is a proper subset of the group.
So otherwise it's trivial subgroup.
Yeah, well, so basically, if we have a group G, then G is trivially a subgroup of G. Also, the singleton set consisting of only the identity element. So this is also a subgroup. So these two subgroups are well, not very interesting subgroups, you know. So yeah. Subgroups of G. Okay. So previously we have given examples of groups. So GL2R is a group of which SL2Z is a subgroup. Right. Okay. So here we have like three conditions for checking a subgroup, but yeah, but one can compactify these three conditions into a single condition. So I'm not going to prove it, but yeah, that's left as an exercise. So H is a subgroup if and only if. So this little symbol here means if and only if. That is, if H is a subgroup, then this condition that I'm going to write now is true. And if that condition holds, then H is a subgroup. So that condition is that for all H1 and H2 in H, H1 star H2 inverse is also in H. So yeah, so this condition combines all the three conditions that I stated earlier. All right. Do you have any questions? Well, if you have any questions at any point, so please feel free to ask.
Is the SL2Z, is it abelian?
No, it's not. Well, I haven't yet said what is abelian groups. Well, so far in the definition of group, we have required that the binary operation is associative. We haven't required that the binary operation is commutative. That is, A star B is not necessarily equal to B star A. So if this happens for all A and B, then we call the group abelian. Okay. All right, now we are going to define what a coset is. So let H be a subgroup of G. Yeah.
So if I constrain myself with one of the elements being an identity vector, one of the elements being an identity vector, then it would be another.
No.
A or B is equal to
Yeah, but for the group to be abelian, this condition has to be satisfied for all A and B. For all elements of the, if we take any two elements from the group G, then if we compose them and if we change the order and compose them, so that two elements has to be the same. So if that happens for all A and B, then we call the group abelian. Okay. Yeah. So yeah, let H be a subgroup of G and take an element from the group G. then we define the set GH, that is the set of all the elements of the form G star H, such that H is empty. So this is called a left coset of H in G. That is, given a subgroup, we are composing all the elements of that subgroup with another element of the group G. Then the set we get, we call that set a left coset, because we are composing that element of the group in the left, in the left of each elements of the subgroup. So this is a left coset. So, well, nothing's stopping us from defining a right coset, right? So we then define a right coset like this: the set of all the elements of the form H star G, such that H is in the subgroup H. So this is a right coset. All right, and so given a group and one of its subgroups, there are like multiple left cosets and multiple right cosets, right? So we take all the left cosets of H in G, and the set we form is denoted by G/H, is the set of all left cosets of H in G. And yeah, so one can write this set like this: GH such that G is in G. Okay, is this clear to everyone? And yeah, similarly, we can form a set of all the right cosets, like, and that set we denote H/G. That is the set of all right cosets. That is HG such that G is in G. Okay, so it's a natural question to ask that if we can make these two sets into a group, if we can define a binary operation on these two sets such that they become groups. So it turns out that this does not happen always. So, but there's a special situation when this happens, and yeah. So now I'm gonna define like what that special situation is. So that special situation is known as the normal subgroup. Like when the subgroup happens to be normal, then these two sets become groups, which we shall soon see, right? Normal subgroup. Okay. A subgroup N of G is said to be normal if for HG in G, so we define a new set now, G and G inverse. So this set is defined as G and G inverse for N. So if this set is the same as the set N, then we call N a normal subgroup of G. Okay, so equivalently we can state this as Gn equals Ng, right? So basically we compose G with G on the right to each element of the set G and G inverse. So equivalently Gn equals Ng. So you see, when N is the normal subgroup,
when you are writing G and G,
yeah,
you mean G star and
right. So when n is a normal subgroup, so this is a left coset, this is a right coset, right? So all the left cosets are automatically right cosets. So then the set G / n and the set n / G are the same, because all the right cosets and all the are left cosets as well, and vice versa. So then we can form a group. So let's take an element from this set G / n or G / n. So so if we take an element from here, so what does an element look like here? So an element in that set looks like of the form GH, right? So suppose we take Gn from here, and we take another element Hn. Okay, and we can define some sort of a composition or a binary operation between these two sets. No, because the binary operation we defined for G was if we are so if we go back to the very first line I wrote here, that binary operation is a map from G cross G to G, right? So now the binary operation I'm defining here, it's a map from G by n cross G by n to G by n. So yeah, so these two binary operations are different, but many textbooks or many resources you find online, they do not distinguish between these two notations.
It's a natural extension of
Yeah.
of the group operation.
Yeah.
I think in mathematics, mathematicians talk about this natural canonical natural problem.
Well, natural has natural has a very specific meaning in category theory. Yeah.
So but you did not write the right answer.
No, I did not. I'm writing it right. So if we take an element G, if we take a left coset Gn and another left coset Hn, so the composition between these two cosets are defined as, it's going to be another coset, right? So it's going to be something n of this form. And what's this? That is G star H. And one can easily check that with respect to this operation, G / n forms a group. Can someone tell me what's the identity of this group? Right. So n is basically En, right? So En and Gn, if we compose these two, we get E star Gn, that is Gn. And you can compose these two in the reverse direction as well, and you find that that Gn compose En is Gn as well. So yeah, so this is the identity element of the group, and given a coset Gn, what is the inverse of this element?
G.
Exactly. So the inverse of this element is G inverse n, and that and well, you can check it easily because that is just okay. And yeah. Oh, I forgot to say one thing, that is G / n is called a quotient. That is a quotient of G by its normal subgroup n. Okay. Is it clear to everyone that the definition of a normal subgroup and the definition of a quotient group?
One thing, G star G from G inverse or bracket and also with binary operator that is star or circle.
Well, circle is the binary operation in the set G / n.
So circle.
No, circle is the operation between these two, and these two are elements of where? These two are in G. And in G, we have a,
G star G inverse square bracket.
oh, this one?
This one and that.
No, this one and that there is no operation.
Just simple.
That's just a coset.
Yep.
And that coset is what you put in front of the coset. That's an element of G.
Right.
And then the normal circle.
So just a representation of it.
All right. So in mathematics, we often study structures. Well, structure is not really a very, very formal word. So so you see, at first we had a set G. Then on the set we've given a binary operation such that certain conditions hold. So we can say that that binary operation is a structure on the set G. So in mathematics, we often study structures by certain maps that sort of preserves the structure. So one such so in the case of groups, the maps that preserves the group structures is known as homomorphism. So that is, if we have a group F, if G is a group under star and H is another group under another group operation, for instance, let's say hash, then this is the map between these two groups. So actually, this is a map between just these two sets, right? So so in order to emphasize that G is a group under the operation star and H is a group under hash, I've written it like this. So this is the homomorphism if f of G1 star G2 equals f of G1 hash f of G2 for all G1, G2 in G. So so if we take any two elements G1 and G2 in G and we compose them, we get another element of G, and that element is so F takes that element to some other element of H, and G. But if we have acted F on G1 first and then on G2 first, then we get two elements of H, right? And on H we have another binary operation hash. So if these equations is satisfied for all G1 and G2, then we call F a group homomorphism. All right. So yeah. So one such example of a group homomorphism is that the map of determinant from GL and R to R minus C. Right. So why is this a homomorphism? So what's the binary operation in GL and R? Matrix multiplication. And what's the binary operation in here? It's multiplication. So if we take any two matrices A and B, we multiply them, then take the determinant. This is equal to determinant of A, determinant of B, right? So determinant is a homomorphism. And another example of a homomorphism is that the exponential map from the set of real numbers to the set of positive real numbers. So the set of positive real numbers is again a group under multiplication, and the set of real numbers is a group under addition. And so why is this a group homomorphism? Because if we take any two elements from the domain set, the domain group R, suppose x and y, and this is equal to exponential of x times exponential of y.
Yeah, and this map is much more stronger than the previous one because
Exactly.
also reverse homomorphism.
Right. So
I think it's called isomorphism.
yeah, it's an isomorphism. So I'm going to define isomorphism.
Means that the two groups are basically the same.
Yeah. Yeah, for all practical purposes, these two groups are basically the same. Okay, so isomorphism. So isomorphism is basically a bijective homomorphism. That is the homomorphism we have, F from G to H. So this is an injective map. Also, this is a surjective map. And if if F is bijective, then we can take the inverse. And the inverse also happens to be a homomorphism. Also, if given two groups G and H, if there exists an isomorphism from G to H, we call G and H isomorphic. Isomorphic. Okay, and we write it like this: G congruent H. So we have just seen that the exponential map is a homomorphism, and well, it's bijective because well you can verify that this is both injective and surjective. So that is there's an inverse map. So what's the inverse map between what's the inverse map of exponential? Logarithm, right? So logarithm is the inverse map, and yeah, so since there is an isomorphism between the group of real numbers under addition and the group of positive real numbers under multiplication, then well, these two groups are isomorphic. So as I said earlier, when two groups are isomorphic, we can basically treat the groups as sort of almost the same groups. Okay. Yes. All right. So I have another definition, that is kernel. So given a group homomorphism F from G to H, we define the kernel of F to be the set, and we write the kernel as ker F. Okay, and this set is defined as all the elements in G such that they get mapped to the identity of H. The identity of H. So the collection of all those elements that gets mapped to the identity of H is called the kernel of F. And yeah, and we have a very interesting fact, that is kernel of F is a normal subgroup of G. And also, so if we have a group homomorphism, there's a very easy way to check that whether the homomorphism is injective. That is, so F is injective if and only if the kernel of F consists of only the identity element of G. So that means if F is injective, then the kernel of F has only the identity element and nothing else. And also, if the kernel of F is only the identity element of G, then F is injective. All right. Yeah. And also another very interesting theorem in group theory that is known as the first isomorphism theorem. So suppose we have a group homomorphism F from G to H. So since a kernel of F is a normal subgroup, we can form the quotient G slash kernel of F, right? And this is a group. Like we have seen earlier that if we have a normal subgroup, then we can form a quotient group. Then we can define a map from this quotient group to the image of F. Well, I forgot to mention what is the image of F. The image of F is basically F of G for G in G, and this is a subgroup of H. Okay, so what does the first isomorphism theorem says? That given a homomorphism F, we can define another homomorphism phi. So how is phi defined? So yeah, so we take an element from this quotient group that is, for simplicity, I'm writing kernel of F to be just K. Okay. So what does an element in this quotient group look like? It's a exactly. So it's a coset. So it's of the form GK or KG because since it's a normal subgroup, all the left cosets are also right cosets. So phi of KG is defined to be just F of G. And you can see that F of G is an element of image of F. So this is indeed a map from G slash kernel of F to the image of F. And the name of the theorem is first isomorphism theorem, but we have defined only a map. So it turns out that this map we defined phi. So phi is an isomorphism. Okay, do you have any questions?
So you create a limitation like less than or equal to something.
Right.
And what would be an inverted triangle for a
Right. So
like before here, you wrote the subset of H. You could write less than or equal to.
so it happens to be a subgroup, but this notation does not mean subgroup, but it happens to be so what Sir just said is that H is a subgroup of G. This is written like H less than like this. And if N is a normal subgroup of G, then we write N triangle G.
So maybe it's a bit outside the scope, but I was wondering, the first isomorphism theorem is your probability proof. Does that also cover groups?
Yeah.
Because the
So this is true for like any groups, right?
so the isomorphism between SO3 and SO2 over Z2 is an example of this.
Right. Okay, I'm not gonna prove the first isomorphism theorem, but I'm just gonna like outline how the proof goes. So sketch of proof. So since the fundamentals of group theory and complex analysis that we will be covering, so they are basically sort of the prerequisites for some of the interesting stuff that we'll see. So we shall prove the interesting stuffs in full details. But for the prerequisites, I'm not going to prove in full details. So for the complex analysis part, I'm mostly gonna just state the theorems and not prove them. All right. So here's how the proof goes. So first of all, we need to check that phi is well defined. So what do I mean by well defined? Well, if we take a coset gk, so in principle, there can be another element of the group G H such that HK and GK are the same. By same, I mean that HK and GK are both the same sets. Then how do we define phi of GK? Is it f of G or is it f of H? So which one? Yeah. So apparently, it turns out that these two are basically the same because the condition GK equals HK denotes that G star H inverse K equals to K. All right. So since the identity element is in the kernel, that is G star H inverse star, the identity element is in this coset, right? So and since this coset is equal to K, then we can write that G star H inverse is in K. So from this you can show that then f of G equals f of H. So phi is indeed well defined. So there's no scope of confusion about the definition of phi. Okay, then we need to check that phi is what? Phi is a homomorphism. So that is, we need to check that phi of GK HK equals to phi of GK phi of HK. So hash is the group operation in the group H. So what is H? If we don't remember, H is the target group of the homomorphism F. All right, so one needs to check this, and then one needs to check that phi is bijective. So checking the surjectivity is very easy because phi is the map from G slash K to image of F, right? So if we take an element from image of F, it looks like from F of G, and F of G and the phi of GK gets mapped to F of G. So for each element of image of F, there is a pre-image of there's a pre-image. So I better write this. Yeah. So phi is surjective, and checking the injectivity is also easy because we have seen earlier that phi is injective if and only if the kernel of phi has only the identity. So kernel of phi equals to what's the identity of G slash K? Right. EK or simply K. Okay, so this is how we prove the first isomorphism theorem. All right, are we all familiar with what a vector space is? So I'm not going to repeat what a vector space is because yeah, everyone seems to be familiar with it. So suppose V is a vector space over, for now, let's say over R. That is the scalars of the vector space comes from the set of real numbers. Okay, and for simplicity, let's say that V is the finite dimensional vector space. So finite dimensional. Then the vector space V has a basis, right? So let V1, V2 up to Vn. This is a basis. So what does it mean? That given any vector in the vector space V, we can write V as a unique linear combination of these basis vectors. That is alpha 1 V1 up to alpha n Vn. And all these alphas come from the field R. That is, yeah, so. And so it's a natural question to ask that, is there an analogous notion of basis in the case of groups? So, so we are going to explore that right now. Now, let's get back to vector space. So, what's the smallest vector space that contains the element V1, that contains the vector V1? What's the smallest vector space? Can someone tell me? Exactly. So if V1 is in a vector space, then all the scalar multiples of V1 must also be in the vector space. So this, and you can easily check that this is a vector space. So this is the smallest vector space containing the vector V1, and we write it like this. Okay, and then the smallest vector space containing V1 and V2 is denoted like this, and what are the elements of that vector space? Exactly. So alpha V1 plus beta V2, where alpha and beta are real numbers. Okay, and well, you can continue like this, and then the smallest vector space containing all the VI's from I running from 1 to n, and that is the vector space V. Okay, now what about groups? Suppose G is a group. What's the, and let's take an element G. So what's the smallest subgroup of G containing this element? So this is, and we write it like this. This is the smallest subgroup of G containing G. Okay, so obviously G is in this subgroup. And well, yeah, E also has to be in the subgroup.
G star G.
Of course. So G star G is also in the subgroup, right? Exactly. And oftentimes we write G star G as G square. That is G star G 2 times. So this is also in G, and G to the n is defined as G star G star G. And there are n many G's. And yeah, so this is also in G, in this subgroup, right? Also, we need all the inverses of these elements, right? So that is G inverse is in that subgroup, and the inverse of G square is also in here, right? And what's the inverse of G square? That is G star G inverse, and it's simply G inverse star G inverse. So we write it like this, G to the minus 2. So this is also in here. So similarly, we can show that G to the minus n is also in here, right? So then we say that this set containing all the Gn's and the identity and G to the minus n's. So one can easily check that this is a group, and this is called the group generated by G. And this group is oftentimes called cyclic group. So cyclic groups are the groups generated by only one element. Okay, and well, yeah. So oftentimes we write E equals to G to the power 0. So you can rewrite this group as G to the N such that N is in set. Okay, and an interesting observation that like, it's not necessary that all these elements that are in here are distinct. So there can be repetitions. Okay. Yeah. So this is the smallest subgroup containing G. That is the subgroup generated by G. Now, what about the case when we have two elements? That is, what about this one? Yeah. So so let's list out like which elements which elements have to be in this subgroup. Obviously, all the elements of the form G to the N, all the elements of the form H to the M, right? And we can combine these two elements. So G to the N, H to the M. Is it all? Is that all? No. We have to take all the elements of this form as well, right? And here, M and N are integers. So this is the subgroup generated by G and H. Yeah. So right. This does not cover all the elements. So I'm just listing which elements must have to be in here. Yeah. So if the group is abelian, yeah, এটা নেওয়ার দরকার, right? So yeah. So you can see that the element, wait, oops, sorry. The elements of the form G to the N, H to the M, G to the K, H to the suppose alpha or something. So the elements of these form also have to be in the group, right? Well, the equality is not really very correct here. So it's this. So how can we like list all the elements in this? Exactly. So what Nian was saying is that the element if we take an element from this group, then that element can be written as one of these two forms. That is G to the power alpha 1, H to the power beta 1, G to the power alpha 2, H to the power beta 2, and this can go on like for finitely many times. H to the power, sorry, G to the power alpha n, H to the power beta n. Yeah. So all the elements of the group generated by G and H is of this form. So one can ask that, what about the elements which start with H? Well, for those elements, we just take alpha 1 to be 0. So there's another way to sort of express this. That is, we can express this as a finite string. Right. So, and all the characters of this string are either G or G inverse or H inverse. So G inverse, H or H inverse. So what do I mean by that? That is, if I have an element like, suppose this is G square H to the minus 3 G H square like this. So you can write this element as G, G, H inverse, H inverse, H inverse, G, H, H. Well, I'm not writing the group operation here, but well, you understand. So this is a finite string, and all the characters of this string are either G or G inverse or H inverse. So this is finite strings with characters G, G inverse, H, H inverse. Okay. So if we have this, then we can define the group generated by finitely many elements, right? So suppose the group generated by G1 up to Gn. So what does this group look like? It also has elements like finite strings, right? So what are the characters of that finite string? Now, exactly. So this is also finite strings, and the characters are either Gi or some Gj inverse. Okay. Yeah. Now, and you can similarly define the group generated by a set. So if S is a set, then the group generated by S is also the collection of all the finite strings. But this time, what are the characters of these finite strings? Exactly. So this is also finite strings such that the characters are S or S inverse for S in S. Well, this S looks like capital S, but it's not. But yeah. Okay. And for some S subset of G, if the group generated by S is equal to G, then we call S a generating set. Of G, or a set of generators. Okay. So is the concept of generating set or group generated by some elements clear to everyone?
Can you give us an example of
Sure.
generating a set?
Okay. The simplest example. Suppose I have the group of integers, and this group is generated by 1. So basically, this group, in other words, this group is generated by a set of size 1, and that set contains only the element 1. Why is that? Because if I take any element from the group Z, then it looks like n. Well, for now, let's say n is positive. Then we can write n as the sum of n many ones, right? Well, one thing to notice is that here in this finite string, I have omitted the group operation here. Okay, so but in Z the group operation is addition, and it goes like this. And if n is negative, then so minus n looks like -1, the sum of n many -1s, right? So yeah. So as I mentioned earlier, that a cyclic group is generated by only one element. So that is Z is a cyclic group. In fact, it's an infinite cyclic group because it has infinitely many elements. So there are finite cyclic groups. If I have to give an example, for instance, exactly. So so there are like 5 complex numbers such that x to the 5 equals 1. So they are placed at here, here, somewhere like this. So these five fifth roots of unities, they form a group under complex number multiplication. And this is a cyclic group because it's generated by, let's say, this element. So if it is 1, it is omega, it's omega squared, it's omega cubed, it's omega to the 4. And yeah, so I said earlier that the group generated by omega looks like the set, omega to the n such that n is in z. But here we have only 5 elements because the omega to the 5 is the identity. Okay. All right. So, yeah. And you see, as I said in the motivating example for vector spaces, so like finite dimensional vector spaces are like really nice spaces, right? So they have finitely many sort of generators, right? So and yeah, but for groups we are not always fortunate because not all groups admit a finite set of generators. In fact, not all groups admit a set of generators as well. Because, well, you can say that a group G is generated by itself. Well, the set G is a trivial generator for G, right? But it's not always the case that there exists a proper subset S such that G equals the group generated by S. So one such example is the group of rational numbers. So the group of rational numbers doesn't have any proper set of generators. Okay, and yeah, so I'm gonna state what the generators for GL2R is. So GL2R is basically generated by the elements of this form: A1, 1A, 1, 1, 1, and 1, 1, 1, where A is a non-zero real number. So yeah, so there are infinitely many matrices here in this generating set. So GL2R is generated by an infinite set. And one can show that this is the minimal generating set. That is, if we delete one element from this generating set, then the set we get, that set does not generate the whole of GL2R.
So this definition of the generator is different from the definition of the generator for a D group. Whereas GL2R is also a D group.
Right.
And there the number of generators is finite.
Well,
but that's a different definition.
Yeah,
Different
yeah.
concept.
I think what you're referring to is the generator of the Lie algebra, right?
That's a basis.
Basis of
But
yeah,
informally, that's also called the generator of the groups. But
Yeah.
informally, but I can see where you're coming from because you are using that many infinite number of times to generate the group.
Okay, I think I mentioned earlier that the group we will be dealing with is SL2Z. And we are very fortunate. Why? Because SL2Z admits a finite set of generators. In fact, the minimal generating set consists of only 2 matrices. So those 2 matrices are one is this. Well, in here I have kept some entries empty, and the empty entries indicate 0. So yeah. and the other one is this. So we shall prove it like later when we will be defining modular forms. So yeah. So SL2Z is like a really nice group that it is generated by only 2 elements.
So it means that any element of SL2Z can be written as multiplication of these matrices
And their
inverses.
Right.
How many times? Any finite.
Yeah, any, yeah,
Finite.
right, exactly. So we shall see 2 proofs of this statement. One is an algebraic proof, another is a geometric proof. But yeah, that's probably like the first or second class on actual modular forms. Yeah, I'll try to cover it in the first lecture on modular forms, where we'll define what a modular form is. Okay. So, does anyone have any question? No? Okay. All right. Now we will define what a group action is. Group action. Okay. A group by itself is basically an abstract object, right? So one can argue that it has like no purpose in life. Okay. But it brings purpose in life when it acts on some set. For instance, like as a motivating example, I can say that we have the group GL and R, right? And this group acts on Rn. Like if we take a matrix from here, let's say M, and a vector from here, then this gives us another vector in Rn, right? Because this vector, we can consider this vector as a column matrix, and this is a square matrix. So yeah, so this is an example of GL and R acting on Rn. And this action has certain properties. That is one very interesting property. Well, both of the properties are very interesting. So the first one is that the identity matrix acting on any vector spits out the vector, right? For all V. And another one is that sort of associativity. That is, if we act a matrix B on the vector V, then we get another vector in Rn, right? Then we can act another matrix on that vector. And this action is the same as the action of the action of the multiplication of these 2 matrices on V. Right. So the action of GLNR on Rn has these 2 properties. So this motivates us to define the action of a group on any set. Okay. So how do we define it? Let G be a group and S is a set, and we say that G acts on S if there is a map, let's say the map is called alpha from G cross S to S. That is, the map alpha takes an element from the group G and an element from the set S and spits out an element of the set S. So just like we have here, we have an element of the group and an element of the set, and we get another element from the set, such that some conditions hold. And also, for simplicity, I shall write alpha of G comma X as G dot X. Okay. Okay, such that such that the analogous statements of these two conditions follow. So that is, the first condition is the identity element acting on any x gives us x for all x in S, right? And the second one is that H acting on X and G acting on that element gives us the same as G star H acting on X. Okay, do you have any question? Okay, another thing is that in this definition, we say that G acts on S from the left. We can also define group actions from right as well. In that case, the map is going to be S cross G to S. But these two situations are basically the same. We're just flipping the order. So, yeah. So we shall mostly be dealing with left action. Okay. All right. And yeah, and we have some interesting subsets attached to this group action. For instance, given an element x in S, the orbit of, we are defining the orbit of x under the action of G is the set G dot x, and that set is defined as all the elements of the form G dot x. That is, in other words, it's the collection of all the elements that x gets mapped to under the action of G. Okay.
Just the last.
Okay. We have defined group action here, right? So what does a group action do? That is, it takes an element from the set and an element from the group, and then it combines them and gives another element of the set, right? And we write it as G dot X to denote that G is an element of the group and X is an element of the set. Now, given an element of the set, we define the orbit of that element to be the following set. That set is like all the elements of the form G dot X. And of course, these elements are in S, right? And all the elements of this from G dot X, and we basically take, vary G over the group G. So it basically means that all the elements of S that it's the set of the elements that X gets mapped to under the action of the group.
An example is like
Yeah.
for the rotation group is the circle. Like if you have a vector x and if you have got the
Right.
group, then the circle is
Right. So, well, I have a different example, but okay, yeah, I'm gonna write this example. So, suppose our set is Rn, sorry, for now, let's say R2, and our group is SO2, SO2R. Okay, so it's basically the set of all the orthogonal matrices and that have determinant 1. So basically, cos theta, sin theta, minus sin theta, cos theta.
It's just circle.
Yeah, that's right.
Yeah, right. And we define the action like in the obvious sense, that is, if we take a rotation matrix, let's say R, and we take a vector V, then we basically so these matrix multiplication is defined as the action of R on the vector V. Now, so this is our space and it's a vector. So this one is our vector. And what's the orbit of this vector? That is, it's the circle, like centered at the origin and that goes through this point. Okay. So yeah, and the example I have written here is that for the action of GLNR on Rn. Okay, so let's say I take the zero vector from Rn, right? What's the orbit of the zero vector? So the orbit of zero, well, it's just the zero vector, right?
It's a fixed point.
Yeah. I haven't defined a fixed point yet, but yeah, we'll need the notion of fixed point. And if we take a non-zero vector here, then what's the orbit of that non-zero vector? Except the zero vector. So this is Rn minus 0. So why is that? Because, well, so we can, so given a non-zero vector V, we can form a basis of Rn where V is one of the basis elements, right? And we can basically define an invertible map that maps V to any of the non-zero vectors. Okay. All right. So yeah, and
Not you going to talk about transitive action.
well,
You don't need it.
no, I don't need it. Yeah. And I need the notion of a stabilizer. So given X in S, the stabilizer of X is defined as the following set. That is, and we write it stabbed X. And yeah, this is the collection of all the group elements such that those elements acting on X gives us X itself. So basically it stabilizes X. So all the elements that stabilizes X. And yeah, and also one can check that this is a subgroup of G. Why is it a subgroup? Because like, obviously E is here because in the definition of group action, we've seen that the identity element acting on an element of the set fixes the element. So the identity is here, and yeah, and given any element G here, G inverse is also here, right? Because G inverse acting on X is the same as G inverse Gx. Because we have taken G in such a way that G is in G. Right? And this is nothing but G inverse star G acting on X. And that in G inverse star G is basically the identity. So that's that. And we can also check the closure. And that's, I'm not gonna check it because it's easy, I guess. Okay. Now, yeah. For the group action, we've seen earlier that the group GLN are acting on Rn. So what's the stabilizer of a vector? So if we take a zero vector from Rn, then what's the stabilizer of the zero vector? it's the whole GLNR, right? And what's the stabilizer of a non-zero vector? Only identity. Okay, we're going to see that now. Okay, well, identity is already, well, identity fixes this element. So we need all the matrices M such that MV equals V. So that is, it's the collection of all the matrices of which V is an eigenvector with eigenvalue 1. So that is, we need basically V is in kernel of M minus I. Right. Well, V being an eigenvector of eigenvalue 1 is equivalent to V being in kernel of M minus I. Okay. So stabilizer of V is equal to the set containing all the M such that V is in kernel of M minus I. Here I means the identity matrix. The M times an identity matrix.
You mean M in GLNR, right?
Yeah. Okay, and to give you all a heads up for what's coming next. So the group action we will be dealing the most in this class is SL2Z acting on the upper half plane. So what's the upper half plane? It's all the complex numbers such that the imaginary part of the complex number is positive. That is this part. So this is the upper half plane. And given a matrix A, B, C, D in SL2Z, so these matrix acting on a complex number Z gives us AZ plus B by CZ plus D. So this is the action, group action we'll be dealing with the most in this class.
Is there any good reason why not changing the whole complex plane?
Well, in order to define the group action, we can take the whole complex plane, but we will be taking only the half of the complex plane for certain reasons that I think. Well, I can say a little bit. That is the complex valued functions that are defined on the whole space, and if the function is bounded, then you can with certainty say that the function is constant. That's Liouville's theorem. So the functions defined on the whole complex plane that are also like differentiable in some ways and bounded. Those functions are not really interesting. So in order to make modular forms interesting, we define them only on the upper half plane. Yeah, so this is a transformation that's called Mobius transformation. Okay, so we are mostly done with the group theory parts. Does anyone have any questions? Also, we haven't verified that this is indeed a group action, and we'll do it later. I'm just giving you a heads up of what's coming next. All right. How much time we have left? Okay. Complex. So I've already said that we'll be dealing with complex valued functions that are differentiable in some sense. So suppose f is a function from an open set to complex to the set of complex number, and U is a subset of complex number, and U is open. What do I mean by an open set? Okay. For defining open sets, I need to define like, open balls first. Like, so this is called the open ball centered at Z naught with radius R, and it's defined as all the complex numbers that are such that that are in distance smaller than R with Z naught. That is, if this is my Z naught and this radius is R, then I can draw a circle, and the interior part of the circle, it's this open. And I'll call a set open if okay,
The circumference is excluded.
yeah, only the interior is included. So this is U. So I'll call U open if I take any element from the set U, I can find an open ball that is completely contained in U. So U is open if for all Z naught in U, there exists R such that the open ball centered at Z naught with radius R is contained in U. So this is what I mean by open set.
In the boundary to one.
Yeah. So this is just for visual references. So this diagram doesn't mean anything. Yeah. Okay. And now I'm going to define what do I mean by the function U to be differentiable. So first of all, we can consider C. Well, C is basically R2, right? Yeah. Well, yeah. Now, for a function like this, defined on an open subset of the complex plane,
Sorry. Sorry for the interruption.
okay. So for f to be differentiable, we need f to be differentiable in the R2 sense, right? So if side note, if g is a function from V to R2, where V is the open subset of R2, then when do I say that G is differentiable? Yeah, so basically, like G has two inputs and it gives us two outputs, right? So suppose the one component of the output is U and another is V. And we call G differentiable if the following conditions hold. That G is differentiable. Well, I'm not writing the whole differentiable word. So I'm just writing this shorthand notation. If all the partial derivatives, that is del U, del X, del V, del X, del U, del Y, del V, del Y, all of them exist and are continuous. So if this condition is satisfied, then we call G differential. All right, but now we have a function from an open subset of the complex plane to the some subset of complex plane, right? So now I can write my function like this: f of x plus iy equals some u that depends on x and y, and I v x comma y. Okay, so as I said, in order for f to be differentiable, first it needs to be differentiable in the R2 sense. That is, like all the partials need to exist and they need to be continuous. But C has one more structure than R2. That is multiplication. So in R2, we don't have any multiplication. But in C, we have a multiplication, and we want our differentiable function to sort of respect this multiplication. Okay. So that's why we are gonna define a new sort of condition for the complex valued functions to be differentiable. Yeah. So I'm defining it right now. So definition: f is differentiable at z0 if the following limit exists. The following limit exists. What is the limit? That is f of z0 plus h minus f of z0 divided by h0 divided by h. The limit of this fraction as h tends to 0. And here, note that h can be complex. Okay, so if this limit exists, we call f to be differentiable at z0. So that is, if this is my point z0, well, not like this, sorry. So I'm approaching h to 0. So I can approach h to 0 like in like any path I want, right? For instance, I can approach h to 0 in this path or this path or this one. Okay, so now for simplicity, first of all, I'm gonna approach h to 0 from the real axis, then I'm gonna approach f from the imaginary axis. So if I approach h to 0 from the real axis, then what do I have? That is yeah, h, if h is real, then this is f of x plus iy plus h minus f of x plus iy. I'm writing z as x plus iy. And dividing h, and we take limit h tends to 0. And here, notice that I'm varying only one of the variables. The other variable remains fixed, right? So this is nothing but the partial of f with respect to the varying variable x at the point z, right? And now we can do it like now we can approach h to 0 from the imaginary axis. Then the limiting value we get is that limit h tends to 0 f of x plus iy plus ih minus f of x plus iy divided by ih, right? And what is this? This is 1 over I del f by del y at z0. So, and this must be the same. Okay. So if we equate these two expressions in the box, what we get is that del f del x at z0 equals to del f del y at z0, and I can take the I up here. Okay. Does this make sense to everyone? All right, and f is basically, sorry, and f is basically u plus iv, right? So using that, I can write it like I del u del x plus I del v del x equals to del u del y plus I del v del y. And if I now equate the real parts and the imaginary parts, I get that del u del x equals to del v del y, and del u del y equals to the negative of del v del x, right? And these two equations are known as the Cauchy-Riemann equations. Okay, but here we have approached h to 0 only using these two paths. So there are like infinitely many choices we have. But fortunately, there's a theorem that assures us that only like approaching from these two paths, like only approaching from the real axis and the imaginary axis is sufficient. That is, so f is differentiable at z0 if, first of all the partials exist and continuous at z0. And the second condition is that the Cauchy-Riemann equations are satisfied at z0. Okay. First of all, we define differentiability as this. Then this theorem assures us that in order to check whether a function is differentiable or not, we need to just check two things. That is, all the partials exist and are continuous. By all the partials, I mean these four partials. Yeah, these four partials. Sorry. So this one, this one, this one, and this one. If these four partials exist and are continuous, and these two equalities hold at z0, then we call f to be differentiable at z0. Okay, our time is over, but I'm gonna end with a very important definition. That is, yeah, suppose f is a function from u to c, and we say u is open. Then we call f is holomorphic if f is differentiable at all z in u.
So for differentiability, you get sufficient condition, right?
No, this is an if and only if condition. Thank you. So by if and only if, I mean that if these two conditions hold, then f is differentiable, and if f is differentiable, then these two conditions are satisfied. Okay. And
Holomorphic does mean differentiable in a complex sense.
yeah. So and holomorphicity is a local notion. By local notion, I mean that we don't say f is holomorphic at a point. We say that f is holomorphic in an open region. Right? So if we have an open region, like an open set, then if f is differentiable at all the points of that open region, then we call f to be holomorphic in that region. Okay, and few examples of holomorphic functions. Well, f from c to c, suppose f of z equals z to the n. So all the polynomials, they are holomorphic. And exponential function. Exponential is defined on complex numbers. We all know that, right? So they are all holomorphic. And f from c minus 0 to c, which is defined as f of z equals 1 over z. This is also a holomorphic function. Okay, so basically all the like nice looking functions that we can think of, they all are holomorphic. So that's basically the gist of the holomorphism. So holomorphicity allows us to have like various sort of nice conditions that we'll be covering in the following lecture. And oh, I need to take the attendance. So